Afternoon, folks. I am hoping that if you are watching this right now, you have already watched part one of my lectures on Enlightenment science. Already kind of introduced some key principles of science in the 18th century. If you've not done that yet, I recommend you go back and watch part one so you have some background for all of this. And if you are in my classes right now, I recommend that you get the handout off of Blackboard so that you can follow along with the terminology and have the names and the dates and so forth in front of you and ready to go. So, spent the first part of this talking largely about the developments of the physical sciences during the Enlightenment, in particular the growth of physics and chemistry as key disciplines that are really making some big headway. We've talked about the so-called pneumatic scientists who are making important discoveries about gases, discovering carbon dioxide and oxygen and so forth, realizing that there's more than one kind of air. We are also talking a bit about the work of the electricians. I don't know if I gave you that term last time, but these scientists who work with electricity call themselves electricians. That's a term that's not going to come to mean what it means today for quite a while. And so a lot of what we've discussed thus far has been clustering around that. Now, I left off last time talking about a fellow named Luigi Galvani, an Italian scholar who gave us the concept of bioelectricity. And Galvani had the somewhat radical idea that electricity was strictly a biological phenomenon, that it was only a thing generated by animals. That idea is one that is going to be at odds with a little bit of electrical reality, and specifically is going to be disputed by a colleague of Galvani's, his friend slash rival, another Italian physicist by the name of Alessandro Volta, V-O-L-T-A. Volta was born in 1745, died in 1827, native of the city of Milan, became professor of physics at the University of Pavia, P-A-V-I-A. In 1775, Volta perfected a technology some of you might have used in your labs, the technology of electrophoresis, and began to do experiments with it. And he makes some important discoveries. In 1776, he discovers methane and proves that some gases, like methane and hydrogen, can be electrically ignited. Important development in chemistry there. He discovers the phenomenon of electrical capacitance in 1791 and begins experimenting with the animal electricity of Galvani. Now, Volta's research has led him to think that electricity is not strictly biological in nature, and he and Galvani have this sort of frenemy relationship where they are both needling each other, but they're also kind of encouraging each other. They write these letters back and forth. They get kind of nasty at times, but they keep replying to each other and criticizing one another's research, but also egging one another on. So it's kind of hard to tell if Volta and Galvani were actually friends or not. But what we can say is that Volta was opposed to this notion that electricity was animal in nature, and Galvani challenged him to find a way to make electricity without a living system to produce it. Volta ends up doing a number of different experiments. He discovers electrochemical series and what's now known as Volta's law of electromotive force. But to prove Galvani wrong, and let me point that out, that is the motive here. He wants to prove Galvani wrong. He begins working on a method to generate steady electrical currents without the need for an animal to make it. By the year 1800, he's developed a device in which he has plates of metal, different metals alternating back and forth, zinc and lead, plates of zinc and lead, sandwiched between plates of copper soaked in acid. Whenever he has those two different metals touching each other through the acidic medium, it ends up generating an electrical current. And Galvani finds that as long as those copper and zinc and lead plates, and his copper later as well, are immersed in this bath of sulfuric acid, that the device will generate a consistent, steady flow of currents, which he could use to route that current wherever he wants it to go. He can run it back through to reverse the oxidation of the metal plates, and he can basically store electricity in a non-biological means with this device. Galvani laughs at it. He refers to the invention as the voltaic pile. Well, The voltaic pile is what you know better as a battery. And that, along with the steam engine, is going to be the other big technology that changes the world. The voltaic pile is the basis of stored electrical current, the ability to generate electrical potentials, store them for future use, and direct them wherever we want them to go without having to capture lightning in a jar. This battery now makes practical applications of electricity feasible, including industrial applications. In our battery-powered world, where many of you are listening to me right now on a battery-powered device, I don't think I need to elaborate further on why this invention is important. And the steam engine and the voltaic pile collectively end up being the technologies that are going to really drive the Industrial Revolution and drive the industrialization of our society as a whole. All right, so we're making some headway. We're starting to merge some chemistry and electricity here in the course of this discussion. Let's bring it all together with the help of a very well-known fellow. I've mentioned him in passing once or twice. You probably heard of him in another class at some point. A guy who comes to be known as the father of chemistry as a distinctive discipline. A Frenchman by the name of Antoine Laurent de Lavoisier. Just a lot of times we just call him Antoine Lavoisier for short. Lavoisier. Lavoisier is born in 1743, dies in 1794. French chemist, often called the father of modern chemistry. Lavoisier came from a very wealthy family. He was quite the child prodigy, entered college when he was only 11 years old to study law and natural sciences. Finished his college education at the age of 15, and at the age of 16 undertook a geological survey of France, making the first geological map of France. He also wrote a paper on effective ways for lighting the streets of large cities. These achievements got him the notice of the French Academy of Sciences, and he was admitted at the age of 25, at that time making him the youngest member. Now, in the French Academy of Sciences, you got a research stipend. You were granted money by the French government to do work. You were granted access to French Academy of Sciences government laboratories. Remember, they were the first scientific society to provide research money for their membership. But there was a string attached. One of the terms of this is that to keep the members loyal, that everybody who was a member of the French Academy of Sciences getting research money from them, by law, had to hold a job as a French civil servant. They had to have some kind of job in the civil service. Lavoisier had a law background, so he was quite suited for this, and the job he ended up having was the position of the fermier. F-E-R-M-I-E-R, fermier. Fermiers were paid tax collectors. They were the people whose actual job, in a time before checks and electronic transmission of funds, was to physically go around and actually collect the money from people for their taxes. Now, the way the French government had this set up is that the fermiers were not given a salary. They were paid a percentage of all the taxes they collected. Theoretically, this was to encourage them to be diligent in their work. I think you can all see why this was a problem. And the fermiers, as a whole, gained a reputation for deep corruption, for skimming off the top, for shaking people down for more than they actually owed, and so forth, as a way of lining their own pockets. As far as we can tell, Lavoisier was an honest guy. He seemed very scrupulous in his record keeping, and as far as we can tell, was not trying to enrich himself at the expense of the job. That said, being a fermier did have a nasty reputation, and it would end up coming back to haunt him. We'll get to that story in a little while. As far as we can tell, Lavoisier did the job strictly because it was the requirement to get in and do the science he wanted to do. He was independently wealthy. He certainly didn't need any money from tax collecting. But with access to the government laboratories, he was able to make some good work. He was assisted in this, I should say, let's give some credit where credit is due, by his wife, Marie-Anne Lavoisier. Marie-Anne Lavoisier was very much his junior. She was 13 years old whenever Lavoisier married her at the age of 31, which was not unheard of in this time. But Marie-Anne Lavoisier actually ended up being quite important to his work. She was well versed in scientific literature. She helped him around his lab, didn't have any publications of her own, but she did assist him with a great many of his experiments, and in particular, she assisted him by translating English language scientific manuscripts for his use. She was fluent in English, he was not. So Marie-Anne Lavoisier does get some credit as a chemist in her own right, although she's not doing independent research. She's working alongside her husband. Now, Lavoisier is having a problem, and namely he feels that the field of chemistry is not well systematized. It is not a well-organized discipline. It lacks consistent terminology. It lacks consistent principles. It needs some systematization. In 1783, Lavoisier does a famous experiment involving a guinea pig. It's actually from this that we get the use of the term guinea pig as a scientific research subject. He demonstrates in the course of this experiment that respiration is actually a slow form of combustion. Lavoisier does this by placing a guinea pig in a box surrounded by ice, measuring how long it takes the body heat of the animal to melt that ice. He then melts the same quantity of ice with fire in order to find out, how long that takes, and he ultimately determines, using careful measurements, that the same amount of energy is involved in each of these exchanges. It's just the combustion reaction is faster than the action of the guinea pig. Furthermore, Lavoisier discovers that when he does burn something, if he carefully weighs the reactants that went in and all of the products that come out, both the ashes left by the fire and the smoke emitted during the fire, he discovers that along the way, you're getting more mass, not less, that you're adding mass through the combustion reaction, which he realizes is because portions of the thing being burned are oxidizing. They are combining with oxygen from the atmosphere. Lavoisier's work not only proves the existence of oxygen, but it lays the foundations of stoichiometry, and it also establishes principles involving the law of conservation of matter. And incidentally, along the way, disproves phlogiston theory. Lavoisier has shown that fire is not an inherent substance present in flammable objects, but that it's simply a rapid oxidation reaction, giving off heat and light as a byproduct. Lavoisier's work is a huge advance in chemistry, giving us a lot of important information about basic chemical reactions, and also, of course, giving us this thing called oxygen. He's one of 3 people who claims credit for discovery of oxygen. Joseph Priestley and Carl Wilhelm Scheele also do. Lavoisier is the one who is going to name it, oxygen. The name given to it by Joseph Priestley was dephlogisticated air, sometimes pure air. Now, Lavoisier is going to go on from here to do a wide range of other chemical experiments, and he's going to summarize his work under a single text called Traité élémentaire de chimie, from the French, Elements of Chemistry, published in 1789. In many ways, Elements of Chemistry is the Principia of the chemical sciences. It does for chemistry what Newton's Principia did for physics. It summarizes a lot of the core principles that chemists of the 18th century have been documenting, introduces the principles of stoichiometry, introduces a formal law of conservation of matter, demonstrates experimentally how the quantity of mass does not change during a reaction, only the form that it takes, explains how combustion works, formally disproves phlogiston, gives more proper scientific nomenclature to a lot of elements, gives these things like dephlogisticated air and inflammable air names like oxygen and hydrogen, actually establishes formal rules and standards for naming chemical elements and compounds. Lavoisier also compiles a list of all known chemical elements in his time, using the definition of elements first proposed by Robert Boyle a century earlier. Lavoisier, incidentally, has 33 elements in his initial list, including a couple that are not, in fact, real elements. He believes that light is a chemical element. He thinks that it's a stream of particles in elemental form. And he also thinks that heat is an element. He defines an element he calls caloric, C-A-L-O-R-I-C. Caloric theory holds that heat is the result of a sort of fluid that moves between objects, getting that object hotter the more that it accretes. And caloric theory becomes sort of a replacement for phlogiston theory after a while. And doesn't last all that long. We're going to see how caloric theory gets overturned in the relatively near future. The Elements of Chemistry establishes the chemical sciences as a distinct field of research and gives a foundation for other chemists to work from later. I should point out Lavoisier himself does not actually discover any new elemental substances, nor does he actually introduce any new chemical procedures. What he is doing is basically showing the systemic unity of the ideas of other chemists and naming things in a more formal way that other people had proposed. Much like Newton's Principia was not all his ideas, it was the synthesis of a lot of ideas from a lot of people. Although, unlike Newton, Lavoisier didn't seem to have any particular problem with giving credit where credit was due to other people, aside from his argument with Scheele and Priestley over who deserved credit in the priority of discovering oxygen, and in that regard, there's reasonable room for doubts. Now, Lavoisier makes a name for himself with this. The French revolutionary governments ends up offering a contract to him. In 1790, he is appointed the head of a commission to devise a consistent set of standards of measurements, not only for science, but for the French nation as a whole. Understand that up till this point in time, pretty much every country had its own standards of measure, traditional standards, units with names like the fathom and the hogshead and so forth, for measuring quantities and distances. The most well-known, of course, being the English or imperial system of measurement, the one that you're well acquainted with, in which we have such arbitrary measurements as 2 cups to the pint, 2 pints to the quart, but for some reason 4 quarts to the gallon, 16 ounces to the pound, but 12 inches to the foot, and 5,280 feet to the mile. If you think about it, it's not terribly logical. Well, Lavoisier, being a man of science and a man of mathematics, decides to arrive at a more consistent standard. And his commission ends up offering a new measurement system, the idea being that all of the units of measurement can be mapped to the physical properties of things in nature, so they can be derived from those natural principles, and that all of the units are named in a consistent way, and all of them follow a progression of powers of 10. That is, every unit is 1/10 of the unit above it and 10 of the unit below it. What I'm talking about, of course, here is the metric system, the basic standard of measurement that is employed by the sciences almost universally today. Metric measurements were first adopted by the French revolutionary government in 1793. It became the standard system used throughout the French Empire. Other European nations were slow to pick up on it, but throughout the 19th century, more and more adopted it, until by the mid-20th century, most of the world was using metric measurements. England was a long-scale holdout, in large part because it was a French idea, and there's this constant English-French rivalry. England still uses a hodgepodge of traditional imperial measurements and metric measurements. If you go to England, you'll measure your height on your driver's license in centimeters, but you still tend to track distances between places in miles. You'll buy gasoline in liters, but people still weigh things in stones. So England is kind of a middle of the road. But that said, the metric system is now the basis for SI, Système International, the International System of Measurements. This is the universal measurement standard employed by all of the sciences. So a centimeter and a hectogram and a milliliter are the same in every country that you go to. All of them are derived from physical properties of nature. You can map a lot of them to water. A 1 centimeter cube holds 1 milliliter of water, weighs 1 gram, has a specific heat of 1 calorie. Now, these days, the metric system is used by almost every country in the world for its day-to-day measurements as well. Aside from England and its kind of mix of traditional and metric measures, every country in the world has fully adopted the metric system, with 3 exceptions. The small Southeast Asian dictatorship of Myanmar, the small Western African nation of Liberia, and, of course, the good old United States, We have been a little behind the times in this regard. We have been quite thoroughly resistant to metric measurements. In fact, whenever the government tried to adopt metric measurements during the 1950s and put up road signs measured in kilometers per hour, people were so opposed they took guns and shot them down. It is my hope that within our lifetimes we see universal adoption of metric measurements. Even now you're seeing food labels carrying them more and more, but I'm not holding my breath. Now, Lavoisier, despite his service to the French nation, came to a bad end. And if you know your French history, you're probably aware that the revolutionary government in France became a little aggressive after a while. The Jacobin governments under Robespierre became violently opposed to the elements of the old royalist French regime and began mass executions as a way of purging the nation of those who were still royal to the French crown. This came to be known as the Reign of Terror. And if you were an opponent, well, you made an appointment with Madame Guillotine, as they called the execution. Now, Lavoisier had arguably been a loyal servant to France, but he had also been a fermier, and the fermiers were a symbol of the corruption of the old royalist French governments. And the Jacobin government decided to make an example. And what better example to make than a very prominent, famous, and wealthy figure who had been part of the corrupt government. And thus it was that Anthony Lavoisier, on May 8th of 1794, had his career quite literally cut short when he was beheaded in Paris, an hour after his father was also beheaded for crimes against the French state. So, chemistry is underway. We've now gotten some basic principles started. We are really moving forward with these chemical sciences. Now, to finish out this lesson, I would like to talk to you all about a couple of miscellaneous scientists, some folks who are doing some other things, some folks who are delving into some areas of research not as tightly mapped to the things that we've been talking about today. And I want to literally travel around a bit for this. I want to pick up some folks from a couple of different geographic localities to give you an idea of not only the diversity of scientific research, but the diversity of topics of research that we are seeing during the Enlightenment. We went far west today. We went to Russia. I'm to Russia, sorry. So, I'm one step ahead of myself here. We went to America for the first time. We introduced our first American scientists. But let's go the other direction. Let's go east. Let's talk about Russia. Now, Russia, I should point out, is considered kind of an exotic realm and is only barely in diplomatic contact with Europe, let alone intellectual contact. There's not a lot of exchange either of governments or of scientific knowledge between them. But there is some. And Russia is making some headway in the sciences itself. The great Russian scientist of the Enlightenment, a very prominent figure in his own nation, he's still well known in Russia today, is a fellow by the name of Mikhail Vasilyevich Lomonosov. Mikhail Lomonosov, Lomonosov, as many O's as you can get in one name. Mikhail Lomonosov is born in 1711, died in 1765. If you were from Russia, you've already heard of him. He's kind of a national hero, great figure, kind of like Ben Franklin is to the United States. Polymath scholar like Franklin, tremendously diverse range of achievements, contributions not only to science, but also to education, art, and literature. But he's little known to us here in the West, and I think it'd be fun to talk about him for a few minutes. Now, Lomonosov is born in a small village called Denisovka on an island at the far north of Russia, just below the Arctic Circle. His father was a prosperous shipbuilder, and he began accompanying him on voyages at the age of 10. Lomonosov was hugely intelligent. He very much desired knowledge. He was largely self-educated, voracious reader. He did not want to follow his father in the shipbuilding trade. At the age of 19, he left home. He was admitted to the Slavic Greek Latin Academy in Moscow. Now, he was not enjoying family support for this. His father had wanted him to follow in the family business, so he had to find a way to pay for his education. And there was a rule at the time, there was a law in Russia, that the children of the clergy, if you were the son of a clergyman, and I say son because women weren't given formal educations yet, but if you were the son of a clergyman, you could attend college for free. So Lomonosov falsely claims that his father is a Russian Orthodox priest. And on that basis, he is admitted to the university for free. He proves to be a tremendously diligent student and completes a 12-year course of study in only 5 years. Partly into it, they actually discovered his falsehood. But at that point, he was such an accomplished student that they said, you know what, we're not going to kick you out. You might as well finish out. So, finishes up his work, gets his PhD, travels abroad to the University of Marburg in Germany, where he studies for a few years to learn some chemistry. Comes back to Russia after spending 5 years of study in Marburg in chemistry and literature and medicine. When he returns home, he joins the Russian Academy of Sciences in the year 1745, becomes their first professor of chemistry, and establishes the first Russian chemistry laboratory. Lomonosov has a wide range of achievements. He, in the year that he establishes that chem lab, is the first person to observe the freezing of mercury. In 1756, he tries to replicate Robert Boyle's experiments with phlogiston and concludes that phlogiston theory is false. He's the first person to do that, well before Lavoisier does, and does not actually discover oxygen along the way, though. And in the West, nobody actually got wind of the fact that he had made this discovery. In the realm of physics, he is the first person to demonstrate a wave theory of light to be correct, an idea that, once again, the West never even hears about that he's done. He is going to get interested in geology, and he's going to discover the organic origins of a number of mineral substances. He realizes that oil, coal, petroleum, and amber are all actually of biologic origin. They're things that started off as living materials rather than non-living minerals. He comes up with an early version of the law of conservation of matter, which again Lavoisier never knows about. He makes contributions to the kinetic theory of gases, which James Clerk Maxwell will elaborate upon a century later. He makes improvements to the telescope long before William Herschel, who we'll talk about in a few minutes, makes the same improvements, and is the first person to realize that the planet Venus has an atmosphere, which he discovers in 1827. He studies iceberg formation, and based on his study of icebergs around the southern hemisphere, he concludes that there must be a central landmass at the South Pole, and predicts the existence of Antarctica, which is not going to be officially discovered until 1820. Lomonosov predicts its existence decades before. He proposes an idea of continental drift, but he offers no mechanism for how it would happen. And he also favors the idea that nature undergoes continuous evolution, although again he proposes no mechanism for how this would function. So Lomonosov has a very vast range of achievements, and I think it was a little unfair to mention all of them, especially given how many things he did before Westerners did them. But again, because of the lack of cultural communication between the West and the East, Lomonosov's ideas were almost completely unknown in the Western world until fairly recently. In addition, he was quite an accomplished artist. He revived the ancient art of mosaic making, which had been done in Greece and Rome, but largely forgotten about since then. He wrote a lot of poetry. He is considered the father of the modern Russian literary language and of modern Russian poetry. Wrote many poems, wrote several, well, not novels, but lengthy works of fiction. He is going to begin, but never complete, an epic poem about Peter the Great, the first emperor of Russia who reached out to the West. Lomonosov actually even gets involved in politics, and in the last year of his life, he becomes the Russian Secretary of State. But he only serves at that post for a year before he succumbs to a bout of flu when he's only 54 years old. So he ends up being one of these figures kind of like Cavendish, who accomplishes a whole lot of things that most people never end up hearing about. Ultimately, his achievements are widely known in Russia. You'll learn about him in school if you go to school in Russia. Here in the West, virtually unknown. So I kind of thought it'd be fun to give him his due. Ooh, hold on one second, folks. Sorry about that, folks. You might have noticed me glancing off to my left here and there. I'm got my notes propped up just out of sight here so I can make sure I'm not leaving out any important details, but I had them propped up against a bottle that I thought was heavy enough for them not to fall over. Turns out I was wrong. But getting back to business. Now, I mentioned in passing that Lomonosov had made improvements on the telescope, which anticipated those made by a much more famous scientist, a guy who you might have heard of if you know anything about astronomy, an Englishman by the name of William Herschel. But we're not going to talk about him by himself. We're going to talk about a pair of scientists together, a brother and sister team. Sir Frederick William Herschel, born in 1738, shares my birthday, November 15th, died in 1822, and his sister, Caroline Lucretia Herschel, born in 1750, dies in 1848. Her birthday, actually, was just a couple days ago as of the time I'm recording this, March 16th. Now, both of them tend to go by their middle names. You'll hear some texts call her Lucretia Herschel, some texts call her Caroline Herschel. He almost always is referred to in texts as William Herschel. He almost never goes by his first name, Frederick. Now, the Herschels, by the way, that last name is Herschel. Now, the Herschels are German, although they spend much of their lives in England. They are natives of the small Germanic kingdom of Hanover. Now, if you know your English history, you might know that the Hanoverian royal family married into the English royal family early in the 1700s. Now, the Herschels were attached to the Hanoverian royal family. Their father was a musician with the Hanoverian Royal Guard. Whenever the Hanoverian royal family married into the English crown in 1755, the Herschels transplanted to England, and Caroline and William were largely going to grow up there. They are both very interested in music, just like their father. William played the oboe, the organ, and the violin, and he was actually quite an accomplished composer. He wrote 24 symphonies during his lifetime, in addition to his achievements in science. His sister was a very accomplished singer. Now, if you studied much music theory, you probably are aware that there are a lot of important mathematical principles involved in that. And the Herschels, through their study of music, got interested in mathematics. And through their study of mathematics, got interested in astronomy. Now, my teaching assistant over here. Anyhow, though, the Herschels, both of them, begin pursuing the study of science and mathematics. And if you've not done so yet, those of you who are in my class and your primary source reader, there's an excellent account by Caroline Herschel about the research she did in tandem with her brother. The Herschels worked side by side in astronomy work. Caroline was relegated to the role of assistant, having to take notes, do calculations on her brother's behalf, and even feed him when he was making astronomical observations, which literally meant sometimes that he was focused on not looking away from his telescope and she would spoon food into his mouth. But Caroline, over time, became more and more invested in the research herself, performing sweeps with the telescope in which she would scan portions of the night sky, taking her own measurements and calculations. And it would be completely fair to say that she was a scientist in her own right, one of the first women to become prominent in the sciences at all. Now, the Herschels are going to make some very important discoveries. William is going to begin building his own telescopes, makes considerable improvements on the telescope, letting him see at much greater distances. During his lifetime, he builds more than 400 telescopes. He and his sister, neither of them marry. They live together. They work on science with most of their time. Now, on March 13th of 1781, an observation is made of a body that they initially call Georgium Sidus, S-I-D-U-S, or King George's star. Georgium Sidus is a body that they realize, wait, this isn't a star. This is a planet. They observe it over several nights, and realized this thing is moving in a way that suggests it is in fact actually a planet. And the Herschels are the first to recognize the planet that, by the way, the planet that they discover has two mispronunciations of its name. Both of them tend to make 12-year-olds chuckle. The proper name of the planet, which you've probably been mispronouncing your whole life too, is Oranos. And the old Greek spelling of it was O-U-R-A-N-O-S, Oranos. Of course, Uranus is the spelling, the pronunciation you hear more often these days. That is not accurate. But yeah, so the Herschels are the first to realize that Oranos is in fact a planet. Galileo had actually observed it. He didn't know it was what he was seeing. He thought it was another star. But they observe it and they're like, yeah, this is in fact really a planet. Now, in all probability, based on the surviving notes, it was Caroline Herschel who made the crucial observation. But science being the misogynistic field that it was, and in many ways still is, it was William Herschel who ends up getting the credit for the discovery of the planets. I would say it's a joint discovery. They were working together on the observations and calculations, but if we have to pin it to one person, Caroline Herschel is the one who made the first observation. In acknowledgement of this discovery, William Herschel is made a Fellow of the Royal Society of London, and in 1782, he is named the King's Astronomer. Caroline, needless to say, does not get either of those things. What she does get, however, is an official salary from the British government as assistant to the King's Astronomer. Yeah, that's a really kind of crappy consolation prize when you discovered a whole planet, but it is kind of a notable moment in the history of science in that she becomes the first woman scientist to be paid for her work. Now, the Herschels continue making observations. They discover two moons orbiting Saturn. For those of you astronomy geeks, it's the moons Mimas and Enceladus. And they also discover two moons orbiting Oranos. And having just attended a performance of Shakespeare's Midsummer Night's Dream after making that discovery, they name them Titania and Oberon. It is not 100% clear which Herschel made which of these discoveries, I should point out. So we know that they were working together on it. In a lot of cases, the notes and notebooks they kept do not make it clear who was holding the telescope at a given moment. The Herschels produce a catalog of nebulae. Nebulas is actually not the right plural. They prove the existence of binary stars, something that had been suggested since the time of Galileo. They demonstrate that the solar system is in fact moving, which will become important to the later idea that the universe is expanding. William coins the term asteroid to describe a non-planetary body in movement in space. And he is credited with the discovery of infrared radiation, which supposedly he did by placing a thermometer outside a spectrum of light split through one of his lenses, putting it outside of the red band, and seeing that the thermometer actually went up in temperature, suggesting there was a form of invisible radiation that was lower wavelength than red light, or longer wavelength than red light, excuse me. The Herschels end up founding the Royal Astronomical Society. William is going to propose that the sun has a hot atmosphere but a cool surface, indeed suggests that it could potentially support life. He actually has a pet theory that all planets contain life of some kind or another. Now, we do not know, as I said, which of the discoveries made by the Herschels can be attributed to William or to Caroline in most cases. In some instances, we can say, yup, this person did that thing. We know that William discovered infrared radiation. We know that Caroline made the first observation of Oranos. And there are a few other miscellaneous things that we know. We know that Caroline Herschel, in the course of her work, discovered no less than 3 comets and discovered no less than 8 nebulae. I got that backwards. Sorry, 3 nebulae, 8 comets. First woman we can definitively say has done this. Now, she is going to outlive her brother. That William dies in 1822. Caroline lives for another 26 years. And she never stops doing astronomy. Anybody who thought that she was nothing but an assistant to her brother is going to be quickly disabused of that notion, because Caroline Herschel is going to continue making astronomical observations and discoveries after her brother's death. thus proving her chops as a scientist. She will retain a salaried position with the British government doing astronomical observations. She is going to update and correct John Flamsteed's star charts, publishing a new version, Historia Celestis Britannica, in 1797, of which she is the sole author. In fact, in 1828, and this is posthumous, unfortunately for her. So 1928. No, it's not posthumous. Posthumous for her brother. Her brother doesn't live to see it. She does. In 1828, 6 years after William's death, Caroline Herschel is going to become the first woman to receive a scientific award. She is granted the gold medal of the Royal Astronomical Society, which is to this day one of the most prestigious awards in astronomy. Caroline Herschel is the first woman to get it, and no other woman is going to receive that medal until Vera Rubin does in 1996, following her discoveries of the proof of black holes. All right. And yeah, I know Stephen Hawking, but Vera Rubin was a crucial figure in that as well. All right, so the Herschels making some headway here, and we're actually seeing a woman scientist, actually for the first time, really getting acknowledgement for her accomplishments. She's never going to get the same fair shake that William does. She certainly is not generally credited in most history books with being the first observation of the planet that she really discovered, but she does actually see recognition for her achievements during her lifetime, which is more than just about any other woman scientist can say. And I'm not saying that this is, a great thing. Clearly, there are other women doing work of this kind quietly in the background in a lot of cases, often as assistants to their brothers or husbands, people like Sophia Brahe or Marie-Anne Lavoisier. But we do start to see little by little, women are making inroads. Women are creeping into the sciences, even if it is as assistants to men, but they're starting to make discoveries of their own. Sadly, it is not going to be until the 20th century that we start seeing a significant contribution by women scientists, and even then, they have to fight for every tooth and nail of recognition. All right, but let's swing back to America for a little while. Let's talk about another American scientist to kind of bring a circle around here, who's going to end up having ties to Germany. We just talked about a German scientist who went to Britain. Let's talk about a guy who starts off British, ends up American, and goes to Germany. A fellow by the name of Sir Benjamin Thompson, although he is more often referred to by his title, Count Rumford, Rumford. Thompson is born in 1753. His birthday is actually, as of the time that I am recording this, in just a day or two. He is born on March 26th. Dies in 1814. He's known as a physicist and an inventor. Now, Rumford is born in Woburn, Massachusetts. He's a native Massachusettan. He is going to be a prominent landowner in his hometown. Starts off as humble means, but he is a social climber. He marries a wealthy heiress and inherits lots of land from her family. Now, Rumford is going to be a fellow who is a rich property owner, supports himself in that way, does scientific experiments basically for his own curiosity. Now, he has an interesting role in the American Revolution because Rumford is going to serve in a militia in western Massachusetts. Now, if you know your American history, you're probably aware that Massachusetts, battles of Lexington and Concord, you know about that, ends up being a critical site in the fomentation of the American Revolution. Indeed, the Massachusetts colony is the first one to erupt in rebellion. Well, a lot of militias end up joining the rebellion. Thompson is an officer in his local militia. Thompson does not like this rebellion thing. He is a royalist, and he is afraid, at a very selfish level, that the rebellion will deprive him of property, that if he throws in his lot with the rebellion, that he will end up losing properties to forfeiture in the aftermath of the war whenever the British inevitably win. So, once the Revolutionary War breaks out, Rumford breaks away from the militia and refuses to allow them to train or quarter on his land as they have been up till that point in time. This, needless to say, does not ingratiate him with the locals, especially given the pro-revolutionary sentiment that pervades throughout Massachusetts. And Rumford is going to find himself in a bad way. His home is actually attacked by a local rebellion, set on fire, and Rumford, showing the kind of courage that would characterize his career, leaves his wife and children to die in the flames and flees to the British side during the war, where he offers his services as an engineer and researcher to General Gage, one of the major commanders of the British forces. During the war, Rumford does a number of different experiments on behalf of the British to improve military technology. He does experiments with gunpowder in an effort to improve its quality. He figures that he is going to ride out the war, get rewarded by the British for his service as a military engineer. And, well, following the end of the war, didn't work out exactly the way that Thompson thought it was going to work out. Forgive me, I use the terms Rumford, Thompson synonymously here, same guy. Now, after this, Thompson, as being an American militiaman who sided with the British during the war, realizes, you know what, hanging out in the United States is probably not a good idea. So he flees to England, remains in service with Great Britain, which, thanks to the Hanoverian royal family connection, has close ties to the Germanic kingdoms, and eventually he ends up performing military engineering service for Bavaria. So, where's the science in all this? Rumford is interested in a lot of different scientific areas, but most of them concern heat. He's very interested in what today we would call thermodynamics, the behavior of heat. And keep in mind that at this point in time, early 1800s, late 1700s, Lavoisier's caloric theory is the dominant model of heat, the idea that heat is a fluid or substance that flows between one object and another. Rumford begins experimenting with ways to conserve heat, to store heat, and to move it around. He's very interested in practical inventions. Among other things, he looks at the insulating properties of various materials like feathers and different cloths and wood and so forth. He concludes incorrectly that air and water are not conductive of heat, but he decides that other materials are much better conductive of heat. In particular, metals and glass, he says, are way better conductors of heat. Now, in 1798, when he's in England, he is working on overseeing the drilling out of cannon bores. The bore is the hole inside of the barrel of a cannon that you put the cannonball down into and then it shoots out of. Now, the way that they cast cannons in those days, a cannon was cast as one solid piece of metal, because if you tried to put it together out of two separate pieces, the force involved could cause them to break apart. So, when you're doing a cannon, you cast it out of a solid mass of metal, and then you drill out the bore. You use a big drill to drill out the bore in the cannon barrel. Rumford was overseeing the drilling of cannon barrels, and he comes to an interesting discovery. Needless to say, for reasons that all of you are aware of, whenever you drill out a big hunk of metal like that, it's going to heat up. Rumford, who's always interested in heat, starts taking measurements, and he discovers that the cannon barrel gets hotter when you drill it out with a dull drill as opposed to a sharp drill. His conclusion is that heat is not a fluid moving from drill to cannon. Rather, he says, heat is an element of friction. And he publishes a text on his findings called an experimental inquiry spelled with an E, not an I, concerning the source of the heat which is excited by friction. And he concludes that heat is a form of motion that is the result of particles present in substances which move faster when they are hotter and slower when they are cooler, and that the more friction you have, the more molecular motion you will create, and therefore the more heat. This ends up disproving caloric theory and also establishing some really important principles in the still young science of thermodynamics. Ends up being an important contribution to the concept of conservation of energy. Now, Rumford is going to continue to be a prolific inventor. Most of his inventions have to do with his research on heat. He does invent the first photometer, the first tool for measuring light, but his heat-related inventions among other things, include improved stoves, the first kitchen range, a double boiler, thermal underwear, and the military invention that got him made a count. He was made a count in Bavaria for his service to military progress for a big invention involving heat. Probably one of the most important inventions of our time, one that many of you all depend upon, namely the drip coffee pots. That particular invention is what he got a Nobel title for, and I think a lot of people would say that's fair. Now, in his later years, Rumford has an interesting life. He ends up marrying Antony Lavoisier's widow. He marries Marie-Anne Lavoisier, and she goes on to help him with his research, just as she helped her first husband with research. So Marie-Anne Lavoisier is an interesting character, kind of moving through both of these stories. Towards the end of his life, he becomes a little guilty about the way that he treated his original homeland. He begins feeling like maybe he didn't do America right. And by way of making up for that, he endows a chair at Harvard University, which is still present today. But he also becomes quite rich from his military engineering, and he decides to put some of that money to use in England as well. He founds an organization called the Royal Institutes of Great Britain, the Royal Institution of Great Britain, or the RI. The RI is an organization dedicated to both scientific research and public science education, sponsors research by its members, and lecture series by prominent scientists to tell ordinary people about how science works. Rumford endows the RI out of his own fortune. It still exists to this day. It's considered something of an honor to give lectures at the RI, and it still does some good research now, including research by several scientists that we're going to talk about over the next couple of weeks. All right, now I've told you today about a number of different people, and in the past couple of lectures on the Enlightenment, I've told you about chemists, I've told you about physicists, I've told you about astronomers and engineers, people researching electricity, people researching gas, people doing a very wide range of things. You might have noticed a trend. A lot of the folks I'm talking about were good at one or two particular things. They were good at physics or chemistry or astronomy. You're not finding the diverse range of interests that you saw in the past. In other words, polymath scholars are not as common as they used to be. And there's a reason for this. The simple fact of the matter is that the body of scientific knowledge that is available has gotten much, much larger. It is becoming harder and harder to be a jack of all trades. It's becoming harder to be a master of multiple topics. There's so much knowledge available that even getting a good solid handle on a couple of them is going to be the work of a lifetime. So you're finding people who do a few related things commonly. If you're good at math, physics, and astronomy are both good fields for you, and if you're doing one or the other of those things, doing both is not hard. They've got a lot of overlap even today. But you might have noted I'm getting more and more specialists over time. Polymaths are becoming rarer and rarer. I talked about Lomonosov, one of the last true polymaths of the 18th century, although he didn't become widely known in the West. But we're talking about polymath scholars, a name that I cannot leave out. Arguably the last true polymath scholar was a rather remarkable Englishman by the name of Thomas Young.